Good afternoon, everyone. We're going to go ahead and get started talking about electrons and atoms, and more specifically, how we got to the arrangement. Now, if you remember at the end of the last unit, we started talking a little bit about electron configuration, and we started talking about orbitals and all that. Basically, we're going to spend some time diving deeper into Bohr and Schrodinger's models. Let's go ahead and jump in. We're going to cover these two standards, 10.9 and 10.18, looking at the actual energy levels and how we figured all this stuff out, as well as how waves and light sort of play into this. Now, first thing we need to start with are the parts of the wave. So, some of these, or all of these, you should have heard at some point, but some of these Greek letters are probably going to be brand new to you. So, first thing we deal with is called the amplitude. Now, the amplitude, again, is the distance from 0, or 0 point, all the way to the crest or to the trough. Now, in either case, this distance is going to be the same. So this is why we're able to determine the amplitude by going crest or trough. Now, the next thing that we look at is the wavelength. This is going to be the distance between two waves, as we see here. So this point to this point represent our wavelength. This will, of course, change depending on the wave, and as we get to learn a little bit more, we're going to start to see relationships between the wavelength and the frequency. The last thing that we're going to deal with, of course, given here, is the frequency. Now, frequency is going to be represented by this thing that looks like a V. It's actually called nu. And it's basically looking at the number of waves that pass a given point in 1 second. Another way that you probably have heard this is someone talking about hertz, or even on your phone it says gigahertz, or 3.5 gigahertz. Sorry, my wife being funny. But this unit is just telling us this is how many waves are able to pass in a given second. So if you have 3.5 gigahertz, that's saying that there are 3,500,000 waves that are able to pass through that processor at a given time. The more waves, the faster it works, the quicker you get to Snapchat and all your other apps and devices. Now, from this, we need to start looking at some relationships. We notice that the product of any wave of frequency and wavelength comes out to a constant, which is c, the speed of light. Now, we may spend a little bit of time talking about and actually calculating these values, but the biggest idea is to see that there's going to be an inverse relationship. Inverse. What does inverse mean? Well, we've talked about this before. Inverse is saying as one goes up, the other goes down. So, if I have a long wavelength, like we're seeing in the first image here, the longer the wavelength, the lower the frequency. Whereas we have the shorter the wavelength, the higher the frequency. This is also going to play a role when we start looking at the amount of energy. But we shall continue. Now, when we look at the different forms of electromagnetic radiation, or light energy traveling as a wave, we have to include all types. Starting from the low end, which is where we're looking at radio waves. This is going to be our lower energy, to gamma waves, which can kill you, on our high energy. Now, one of the ways that you can remember these different types of waves, we have 7 different types, is to remember the following mnemonic. Red Martians invaded Venus using X-ray guns. This is actually going to come in kind of important in the next couple of slides, and you'll understand a little bit why. When we look at this spectrum of light, of energy overall, we note that all electromagnetic radiation travels at 2.998 times 10 to the 8th meters per second. This is the speed of light. So it doesn't matter what the value is in terms of the wavelength or the frequency. When we multiply them together, they have to come out to this value. This is going to make our calculations very easy, but it also puts into perspective how energy actually works. Now, if you look toward the middle of our little diagram here, you get what we call visible light. These are the colors that you and I see on the everyday basis. These are the ones that are reflected when we look at people's clothing, shoes, cars, the trees outside, all of those different things. And it's made up of this very, very narrow band of energy on the entire electromagnetic spectrum. Now, there are some types of energy that we use on a regular basis. Radio waves, if we listen to the radio in the car, or many times even looking at infrared technology, microwaves, literally using a microwave to heat up your food, you're using different types of radiation. This is why they say don't stand in front of the microwave. It can eventually do damage. Infrared, when you turn on the TV using a remote. Ultraviolet, coming from the sun and the atmosphere. X-rays, when you go to the doctor, and so on. All of this is just a form of energy that we're able to experience in these different forms. And so as we continue to look at light and the relationship between wavelength and frequency, all those types of things, it leaves us to ask a very, very simple question, which we'll get into in just a second. Now, if you go back to the slide we were just on, note that where we had the frequency, it was very, very long, radio waves, we're exposed to those on an everyday basis. They don't really do any damage to us. Right now, you're probably sitting there and there's some flowing right through you. You would never know. But as we get further and further to the right, or towards our gamma rays, these are the short wavelengths. These are the ones that can get inside of your DNA and scramble things. Well, we found that there's also a relationship between the frequency and energy. And we found that it's a direct relationship. So, the higher the frequency, the higher the energy. The lower the frequency, the lower the energy. This is the reason why you don't die right away from radio waves. Okay? Now, prolonged exposure to many things will start to eventually cause problems. But, at the rate that you're going right now, I think you'll be fine. Now, the grand question that you all are probably asking, why do we care about light and waves and all those different types of things? How does it relate to chemistry and what's going to be on my test? That's usually what we're thinking. So, when we looked at Rutherford's model, it left some gaps for us. It told us, this is how the atom is arranged. We have this dense nucleus in the center. Everything looks good. But it didn't actually explain the chemical properties of the element. For example, if you look at the image here on the screen, you'll notice that we have a part of this iron that seems to be glowing orange and another part that's glowing yellow. Why does that happen? How did we come up with the fact of, to explain why and how this happens? And this was one of those gaps that Rutherford kind of left us with. In comes our good buddy Bohr. Now, he was actually a student of Rutherford, so student surpassed the teacher. Now, he started exploring, how the energy level or energy amount of an atom changes when we hit it with light. This is one of the things that was originally explored by Max Planck. We'll talk about him a little bit and how we calculate the energy of the photon. But the basic idea was, if I have an electron like we see these here on the screen, when I hit it with energy, it's going to cause it to go up to a higher level. Now, this excited electron will stay there for a little bit, but it's going to be attracted back towards the nucleus. And when it comes back down, it's going to release some light. Depending on how far it goes, that's going to help us to start figuring out the distances and the type of light that's going to be released. Now, Bohr figured out that with his demonstration and his studies, that it was like rungs on a ladder. If I have a ladder, most of us have seen one before. Usually we have these evenly spaced steps. Now, if I'm standing on the ladder, I can't actually stand in between the steps. I have to stand on one step or the next. In his explanation, Bohr started to realize that, hey, these energy levels are what we call quantized, or they're at set energies. An electron can't be found at energy level 1.5. It can only be at 1, or it can be at 2. To give the general idea of his findings, let's take a look at the first one. Now, in the first example, we have regular light. It's just regular incandescent light bulb. Now, when this is shined through a prism, we get what we call a continuous spectrum. Now, this continuous spectrum shows all the different wavelengths of light. He noticed that when he took another type of element, in this case helium, and did the same thing, we didn't get the same continuous spectrum. We actually got what we call the atomic emission spectrum. Oops. Now, this is going to be different for each element. So this is helium spectrum. There's going to be a slight shift in what we're looking at for hydrogen or for lithium or so forth. So we don't get this nice continuous band, but we actually get these different, what we call discrete lines. Each of these lines is represented by an electron energy. Because again, wavelengths, light, this is where it starts to come together. So, when they absorb that energy, they move up, and then when they come back down, they release the energy. Depending on the color of wavelength of light, we can actually calculate how much energy or how far the electron moved. The farther they fall, the more energy is released. These are where a couple of scientists started looking. We have the Lyman series, where a lot of the values that they were finding were in the ultraviolet range, and that's why it was very difficult to see. We have the Passion, which a lot of them were in the infrared, and the Balmer series, where a lot of our transitions were found in the visible range. This allowed us to be able to actually see and calculate the amount of energy lost in each of these cases, giving us a better idea of the actual fixed energy levels that Bohr had been speaking about before. Now, the question is, where do we go from here? And we're going to leave that for the next video. We're going to go ahead and wrap this one up, and we'll talk in class. Have a great day.